Okay, so we have in the last, I don't even know what we did. In 4 and 5, we've come up with this idea that we can create an area function, tells us the area under a curve from any starting point to a stopping point that we input into the area function. So I think we started at 0, is that true? Yeah, we started at 0, but you don't have to. It's still an area function if you want to start all of them from 1. They do all need to start in the same spot for this to be our area function. So if we built an area function along the lines of this right here, g of x equals the integral from a to x of some function, our claim is, and this is entirely based on looking at some graphs, that this g of x function, this area function, is an antiderivative of f. And I want to now check and see if that is actually true. So if we want to check this, really what we need to know is the derivative of g equal to f? So is g prime of x equal to f of x? And if so, then the area function is an antiderivative. If the derivative of the area function is little f, then the area function is the antiderivative of little f. Okay, so we have to go all the way back to the beginning of calculus, which makes me super happy. It might not make you super happy, but I love it. If we want to take the derivative of a function, and it's not some nice function that we have shortcuts for, we have to go back to the limit definition. So we're going to say that g prime is equal to the limit as h approaches 0 of g of x plus h minus g of x all over h. And we can do a little better because we do have a definition of this g, this area function. So we know that g of x plus h is the integral from a to x plus h of f of t, and g of x is the same as the integral from a to x, f of t dt, sorry it's scrunched, all over h. And then we can actually simplify that a little bit using our properties, but I'm even going to draw a picture because there's lots of variables, so I don't want to lose anyone. I'm going to say, let's just pretend that this is what g looks like. And this could be our a, and this could be our, here, I don't like my g because it gets really vertical at the end, and I want it to not be. And this could be our x, and this could be our x plus h. X plus h could be left or right of x, depending on whether your h is positive or negative, but I'm just going to draw it right for now. It doesn't make any difference in the argument I'm about to make. Okay, so if we are looking at first the integral from a to x plus h, so we add up all of this, and then we want to subtract off the integral from a to x, so we get rid of all of that. What we will be left with is just this little chunk right here. So really what we're ending up with here is the limit as h approaches 0 of the integral from x to x plus h of, oops, not g, goodness, f of t dt all over h. Okay, so first step. But I want to go further than this. I want to look at my picture and say, okay, well, this little strip is h units wide, and we're letting h get really small. So even in this picture where h isn't infinitely tiny, I can see that I should be able to do a really good job of estimating the area of that strip with a little rectangle. And the skinnier that little strip gets, the more perfect that estimate is going to get. So basically, this little strip that we're looking at should have area, which is what the integral represents, that's equal to h times f of x, or f of x plus h, all the same as these get infinitely close together, but I'm just going to use f of x. So we really are looking at the integral represents area, so h times f of x, and then we're supposed to divide by h, and the h cancels out, which is beautiful because as h goes to 0, nothing at all happens to f of x, and I just get f of x. So I have just verified using my classic limit definition that you all didn't like earlier, but is amazing, to verify that the derivative of the area function is in fact the function whose area you are accumulating. So it is true that if you build an area function, it is automatically, no questions asked, the antiderivative of whoever's area it's calculating, which is pretty awesome. I don't know if it seems awesome, it's pretty awesome. Let me sidetrack for just 1 second. I was going to point out that if you say, well, I wasn't going to say that the height of the rectangle was x, I was going to say it was x plus h. I want to do a right instead of a left-hand sum in this picture. No big deal, because as h goes to 0, that's still going to give you f of x. Okay, so why is this so exciting? This really ties together this whole idea that integrals are the inverse operation for derivatives. We said that really early in the quarter, and I don't know if I've really carefully said it back to you again since then or not, but I'm going to right here. So we know that antiderivatives are the inverse operation for derivatives, the inverse process. We have given antiderivatives an integral name, so we know just by the way we made them that indefinite integrals are the inverse operation, the inverse process for derivatives. We then created these definite integrals, and we know that definite integrals are related to indefinite integrals or antiderivatives by the first part of the fundamental theorem. So if we want to find a definite integral, we find the antiderivative, we plug in the endpoints, we subtract. What this is saying is that really the definite integral is also an inverse operation for differentiation. So now we can make this function by building a definite integral, an area function, and it is automatically an antiderivative. So again, integrals, even these kind of funny definite integrals, and derivatives really are inverse processes. They do the exact opposite of each other. So this is a big deal. So I am just going to try and summarize because people always walk away from this section, I think, kind of having a hard time seeing what the big point is. So here's the big point. The big point is that the area function is automatically, no questions asked, an antiderivative. Integrals, definite or indefinite, and derivatives are inverse processes. So if you build a function using an integral, it is automatically an antiderivative. That's the opposite of building a function by taking the derivative. I do want to sidetrack really quickly because I promised I would. You may or may not care. But we claimed earlier, and I didn't verify it, that the integral from a to b of little f of x, I'm going to stick with my t's. I can't think right now if I need to or not, but I'm going to for now, is the same as taking a big F of b minus big F of a, where big F is any antiderivative. Big F prime is equal to little f. And now that we have this second part of the fundamental theorem, it makes it actually pretty quick to verify this. So we intuitively went through, I don't think it's a big stretch to believe this, but I do actually want to verify a little bit. So let's just say we have our area function. Let's start with that. So let's let g of x be, and I'm going to go 0 to x. It doesn't matter, but that's the specific one. Actually, I'm not. I'm going to go a to x. I like that. Of f of t dt. And we know now that this is an antiderivative of little f. And we're going to let f, big F, be any other antiderivative of little f. Of little f. Okay, so now we have two antiderivatives, big F and big G. So we know, based on what we've been saying all along, that, which order do I want this in? I don't know if it matters, that g of x and f of x only differ by some plus c. So we know this. Okay, so now we're going to try plugging some values into our g of x and comparing with what this statement says about those values. So for example, if we plug a into g of x, using the definition, the first definition, so using number 1, we know that that's the same as the integral from a to a of f of t dt, which we know automatically is 0. We also know from number 2, did I number that one? Number 2, that g of a is equal to f of a plus c. So now we know that f of a plus c is equal to 0, which implies that, which one do I want to solve for? C is actually the opposite of f of a. So if we go back up here, we can now say that g of x is equal to f of x minus f of a. Okay, and then if we really want to wrap this up, we need to try g of b. So we've got a little information. We know from number 1 that g of b is the same as the integral from a to b of f of t dt. We don't know that that's 0. We don't have any easy conclusion to draw, but we can compare to number 2 and say, okay, well, according to number 2, which is, we have a new and improved number 2 now, this should also equal f of b, because we plug b in for x, minus f of a. And this is exactly what we were hoping to claim, that the definite integral from a to b of little f will in fact equal any antiderivative evaluated at b, and then evaluated at a, and then subtract. Okay, so we've got our fundamental theorems. Again, big thing to realize is this verifies antiderivatives, integrals related. Derivatives, integrals, inverse processes. So any integration in a problem means you're doing something that is the inverse of a differentiation. That is the big deal. Thanks for watching.